use this idea of solubility rules as a way of predicting whether or not an ionic compound will be soluble. And so we can look at a structure and know that this iron 3 nitrate will be soluble, whereas this hydroxide will not, based upon our solubility rules. All alkaline metal salts are soluble. All nitrates are soluble. All halides are soluble, except silver, lead, and mercury 1. These halides are not soluble. Pretty much everything else is insoluble. Again, there are exceptions, but for the most part, all hydroxides are insoluble, except those that hit one of the other rules. Now, what that means, though, is that if we mix two aqueous solutions, what happens from our discussion is we know that this aqueous sodium hydroxide is really composed of sodium ions and hydroxide ions, and they dissociate if they're soluble. And the same would be true with the iron and the nitrate. And in this case, there would be actually 2 nitrates. But for the most part, we're just going to ignore that. What happens then if you mix these 2 solutions? Well, the solubility rules still are in effect. And as I mentioned, if a reaction is not going to proceed one way, that means it'll likely proceed the other. If you were to mix these materials, the hydroxide iron and the iron ions would interact and combine to form the iron hydroxide compound, and it would precipitate out a solution. These are precipitation reactions. So solubility rules indirectly also tell us which reactions will take place. And the way we look at them is we compare the cation of one and the anion of the other. Right? These other materials are what we call spectator ions. Now, how do we figure this out? The easiest way is to sort of use what we call molecular equations, ionic equations, and net ionic equations. These allow us to predict whether or not a system will and what the formula of that material will be. So these are predictive tools, and we use those predictive tools to calculate formula of the ionic compounds, which, as we know, leads us to stoichiometry. So, how do we use the molecular equation? Well, the molecular equation, going back to this iron, the molecular equation is the overall reaction. What happens? We mix our sodium hydroxide, aqueous, plus our iron 2 nitrate, also aqueous, and there's a reaction that proceeds to form iron hydroxide plus and whatever's left over in solution. Now, this iron hydroxide precipitates out as a solid, everything else remains in solution. This is an unbalanced equation, so if we balance it up, then it would be a molecular equation. 2 sodium hydroxides, 2 Na, 2 NO3. And we could also simplify this as 2 Na, NO3 aqueous, though we may not want to. This is our molecular equation. It tells us overall what's happening. But how do we generate this? I mean, how did I know that that hydroxide formed? And how do I know that we had that sodium nitrate? So this molecular equation is actually the end result. Our goal in this process is to generate molecular equations or net ionic equations, depending. Let's see how that works. For this, we turn to the Ionic equation. The Ionic equation is probably the most informative. So let's take a look at an example. So we have some silver nitrate, aqueous, plus some potassium dichromate, also aqueous. And you mix them together and you want to predict the products. A typical question would read, if you mix these, what would be the precipitate? And then where we're going from there is, if you mix these, how much would precipitate and what? This also answer could be nothing could precipitate. How would we know? So the Ionic equation is used to predict what's going on. In the Ionic equation, you break everything down into the individual ions. In the Ionic equation, we take our silver nitrate, we know that it's an aqueous silver ion and an aqueous nitrate ion, plus a couple potassiums, in this case 2, okay, plus aqueous, plus Cr2O7 minus 2, also aqueous. And then we put into action our solubility rules. Our solubility rules say that all halides are soluble except some silver salts, all nitrates are soluble, and all sodium salts, all alkali metal salts are soluble. All right, good. Start comparing ions. We compare the cation of one with the anion of the other. And so if we take a look at this anion and this cation, we see that this is a potassium salt. All potassium salts are soluble. All alkali metal salts are soluble. So that means that whatever that potassium is paired with will probably be a soluble pair. Then we compare the chromate to the silver salt. Now, I don't remember anything specific about chromates in our solubility rules, but pretty much everything that isn't on those top threes is going to be insoluble. This would form a new compound, which we would then balance out in the correct formula. We know that silver has a +1 charge, the chromate has a -2. That would require 2 silver, Ag2, Cr2O7, would precipitate out as a solid. So now this is our precipitate. We redraw that over here on the product side. Ag2, Cr2O7 as a solid, leaving in solution the potassium and the nitrates. Now, this is not yet balanced, and so we can go back and balance it, and we see that to create this, we would require 2 silver, and that would require 2 nitrates, plus 2 potassiums, plus Cr2O7 to generate Ag2, Cr2O7, plus 2 potassiums, plus the 2 nitrates. Now this would be a balanced chemical reaction. We could then simplify this back to 2KNO3 if we so desired. This is the Ionic equation. Break everything down into its ions, see if anything combines, balance. Now the Ionic equation gives us a lot of information. We can also use it stoichiometrically. But there's another, we can then take this ionic equation and recombine it to make the molecular equation, which we did with the potassium. Aqueous, Ag2Cr2O7, it's a solid, K2Cr2O7, aqueous, by combining everything back to our starting conditions. So this would be the molecular equation. The ionic equation tells us the molecular equation. And then we could use this for our stoichiometry. So the molecular equation is pretty good for our stoichiometry because it's like what we do in the lab. We'd go to the lab, we'd weigh out some silver nitrate, we'd have potassium chromate, we'd get so much of the solid out. All right, so nice and predictive. We could then use this formula here to calculate its molecular weight and go with that. Stuff we've been doing up to this point. But there's another hidden piece of information in here. If we look at the ionic equation, we'll see that there's some potassium on both sides and some nitrate on both sides. And if you remember anything from math, when you have the same thing on both sides of the equation, they cancel out. So we could cancel out these potassium and these nitrates, leaving us with the following, a simplified formula that we call the net ionic equation. The net ionic equation is all of the ions not directly involved in the reaction, silver and chromate, precipitating out the silver chromate, are eliminated. These are called spectator ions, because they just sort of sit around and watch. They don't play a direct role in the chemistry. Now, that's not exactly true. We'll learn about that later in analytical chemistry. But for the most part, they are spectators and they don't directly impact us. We could substitute any ion that was a soluble ion and we'd get the same basic chemistry. 2 silvers plus the dichromate give us this solid silver dichromate as a reactant. So the net ionic equation eliminates all the spectators. And it's also useful, it's generic. Every time you have a silver ion and a chromate ion present in solution, they're going to make this silver chromate. So it doesn't matter what the source of the silver ion, doesn't matter what the source of the chromate. So these are predictive. We can use these ionic equations to predict whether or not something will happen. So you should be able to draw the ionic equation and the molecular equation from 2 predictive sets of compounds.